Hello, friends. Enrico Fermi, born in 1901 in Rome, Italy, came from a family of middle-class professionals. His father, Alberto Fermi, was a successful official in the Italian Ministry of Communications, while his mother, Ida, was well-educated and came from a family of prominent academics. Fermi's early exposure to books and intellectual discussions in his household fostered a natural curiosity and love for learning. By the time he was a teenager, he had already demonstrated a keen interest in the sciences, especially physics and mathematics. Fermi's academic journey began at the University of Pisa, where he studied engineering. His brilliance was evident early on, and he quickly moved beyond basic coursework to explore more advanced concepts in physics. Fermi's education was deeply shaped by the intellectual climate of the early 20th century, a time when major advancements were happening in the world of physics. The development of quantum mechanics, the discovery of the electron, and Einstein's theory of relativity were reshaping the scientific landscape. As a student, Fermi was drawn to these revolutionary ideas, and his work would eventually make an important contribution to these emerging theories in 1922. After completing his undergraduate studies at the University of Pisa, Fermi moved to the University of Florence for his graduate studies. There, he began to develop his expertise in theoretical physics. Fermi's academic talent quickly gained the attention of leading scientists, and his insights were increasingly respected within the. While in Florence, he worked on a variety of topics in physics, but it was his work on quantum mechanics that earned him significant recognition. He applied the new principles of quantum theory to explain the behavior of electrons in atoms, an area where classical physics had struggled to provide satisfactory answers. At just 25 years old, Fermi published a groundbreaking paper on the statistical behavior of particles, which would later become known as the Fermi-Dirac statistics. This theory helped to describe the distribution of particles that obeyed certain quantum rules, and it was an important advancement in the field of quantum mechanics. Fermi's work was initially part of a larger effort to understand atomic structure, but it quickly gained traction and would later be crucial in explaining phenomena like the behavior of electrons in solids and the properties of atomic nuclei. Fermi's early career was shaped by the mentorship of some of Italy's leading physicists. He studied under the guidance of the renowned Italian physicist Luigi Puccianti and quickly gained a reputation as a serious, focused researcher. Fermi's brilliance didn't just lie in his ability to understand existing theories. He also had an incredible knack for formulating new questions that pushed the boundaries of what was known. In 1926, Fermi was appointed to a faculty position at the University of Rome, a move that would significantly enhance his career. It was here that he began to gather a group of talented students and collaborators who would help him carry out some of his most important experiments. His early years as an academic were marked by a drive for perfection and a relentless pursuit of knowledge. Fermi's ability to solve complex problems and his innovative approach to research earned him the admiration of his peers. By the late 1920s, he was already considered one of the leading physicists in Europe. However, Fermi remained humble, always quick to credit the ideas and input of his colleagues. His work ethic and intellectual rigor were evident in his lab, where he was known for his thoroughness and attention to detail. Throughout his early life, Fermi was not just an academic. He was also deeply invested in the broader questions about the nature of the universe. His academic experiences set the stage for his later revolutionary contributions to the world of nuclear physics. They were also integral in shaping his approach to problem-solving and scientific inquiry, a trait that would continue to define his work throughout his illustrious career. Enrico Fermi's contributions to nuclear physics were nothing short of revolutionary, and his work laid the groundwork for numerous advancements in the field. One of the most important aspects of Fermi's legacy is his pioneering work with nuclear reactions, which began in the 1930s. His research in this area fundamentally changed our understanding of atomic particles and the behavior of subatomic particles. In 1934, Fermi made a groundbreaking discovery that would go on to shape the future of nuclear science. He was the first to demonstrate that slow neutrons could be used to induce nuclear reactions in certain elements, particularly in uranium. This discovery had far-reaching implications, as it revealed the potential of neutrons as a tool for initiating and controlling nuclear fission, the process by which atomic nuclei are split, releasing vast amounts of energy. Fermi's work in this area earned him the Nobel Prize in Physics in 1938, recognizing the significance of his research in advancing the understanding of nuclear phenomena. What set Fermi apart from many of his contemporaries was his ability to combine theoretical physics with experimental techniques. Fermi's expertise in both realms allowed him to conduct precise experiments and draw conclusions that would later become central to the development of nuclear technology. He created what became known as the neutron bombardment technique, in which neutrons were directed at various elements to observe how they reacted. This method enabled Fermi and his collaborators to identify new elements and study their nuclear properties in ways that had never been done before. Fermi's research also led to the discovery of the so-called nuclear chain reaction, a process by which the fission of one atomic nucleus releases neutrons that can then induce further fission reactions in neighboring nuclei. This concept would later play a critical role in the development of nuclear reactors and atomic bombs. Fermi's early recognition of the potential for controlled chain reactions set the stage for later efforts to harness nuclear energy, both for peaceful purposes and for military applications. In addition to his work on fission, Fermi made significant contributions to the understanding of beta decay, a process in which an unstable atomic nucleus emits an electron or positron. Fermi's theory of beta decay, known as the Fermi theory of beta decay, provided an explanation for the process by incorporating the weak nuclear force, a force that was still not fully understood at the time. This theory not only helped explain beta decay, but also contributed to the development of the broader field of particle physics. Fermi's contributions to nuclear physics were pivotal in shaping the trajectory of 20th century science and technology. His work laid the foundations for both nuclear energy and the development of atomic weapons, two advancements that would have profound global consequences. His ability to bridge the gap between theory and experiment, combined with his relentless curiosity, made him one of the most influential figures in the history of science. Enrico Fermi's involvement in the Manhattan Project was a pivotal moment not just in his career, but in the broader history of nuclear physics and warfare. After his emigration to the United States in 1938, Fermi quickly became a key figure in the scientific community. The increasing fear of Nazi Germany's potential to develop an atomic bomb catalyzed the formation of the Manhattan Project in 1942, a top-secret U.S. government initiative to build the world's first nuclear weapons. With his profound expertise in nuclear reactions, Fermi was recruited to contribute to the project and played an instrumental role in its success. Fermi's primary contribution to the Manhattan Project was his leadership in the creation of the world's first nuclear reactor, Chicago Pile 1B1. The development of the reactor was an essential step in demonstrating that a controlled nuclear chain reaction, where the fission of one atom could trigger the fission of others, was possible. This chain reaction would be the foundation for both nuclear energy and the atomic bomb. The experiment was conducted under the stands of the University of Chicago's football stadium in December 1942 in a makeshift laboratory that was both rudimentary and highly secretive. Fermi's brilliance and leadership were critical in designing the reactor, which used uranium and graphite as its primary materials, The Chicago Piala 1 was built to be a simple but effective reactor, relying on a self-sustained chain reaction to release energy. The successful initiation of the first controlled nuclear chain reaction on December 2, 1942 marked a monumental achievement in scientific history. The experiment lasted only about 28 minutes, but proved that nuclear energy could be harnessed for practical purposes. This momentous event not only validated the scientific principles underlying nuclear fission, but also opened the door to the possibility of building nuclear bombs and power plants in the future. The success of Chicago Piala 1 directly contributed to the subsequent advancements in both nuclear weapons and energy. Fermi's reactor demonstrated that nuclear reactions could be sustained and controlled, leading to the development of the plutonium bomb, which was tested in the desert of New Mexico in July 1945. The atomic bomb that followed was the product of collaborative efforts from many scientists, but Fermi's understanding of neutron behavior and his work on chain reactions made the realization of this weapon possible. Beyond his work on the reactor, Fermi's scientific acumen was integral to solving the many technical challenges of the Manhattan Project. His deep understanding of nuclear physics enabled him to offer critical insights into issues such as neutron moderation and critical mass, which were necessary for his leadership and ability to solve complex problems under pressure earned him respect and admiration from his colleagues, many of whom considered him a central figure in the project's success. Fermi's role in the Manhattan Project, while pivotal, was not without moral conflict. He later reflected on the implications of atomic weaponry and the devastating power it represented. However, during the project, his focus was on the scientific and technical challenges at hand, aware of the potential that nuclear energy held in altering the course of the war. Ultimately, Fermi's work in the Manhattan Project helped bring about the end of World War II, but it also initiated the nuclear age, an era fraught with both promise and peril. The creation of Chicago Piala 1 was one of the most significant achievements of Fermi's career, establishing his legacy as one of the central figures in nuclear physics. The implications of his work reverberated across both scientific and political realms, shaping the development of nuclear technology for years to come. Enrico Fermi's legacy extends far beyond the laboratory, as his influence has shaped not only nuclear physics, but also the broader landscape of scientific discovery and technological advancement. Fermi's profound contributions to the development of nuclear energy, particle physics, and the modern understanding of atomic structure have made him one of the most influential scientists of the 20th century. Fermi's most enduring legacy lies in his work on nuclear physics, particularly his role in the development of the first controlled nuclear chain reaction. His contributions to the Manhattan Project and his work on nuclear reactors laid the foundation for the atomic age, marking the beginning of both nuclear energy production and the era of atomic weaponry. Although the use of nuclear bombs in Hiroshima and Nagasaki remains a subject of intense moral debate, Fermi's pioneering research made possible the understanding of how to harness atomic energy in both destructive and constructive ways. His ability to bridge theoretical physics with practical experimental work paved the way for countless innovations in energy production, medical treatments such as radiation therapy, and even space exploration, where nuclear-powered systems are sometimes used for long-term missions. Beyond his work on fission, Fermi also made key contributions to the understanding of particle physics. His theories and experiments contributed to the discovery of various particles such as the neutrino and the pion, and his work provided essential insights into the weak nuclear force. Fermi's formulation of Fermi-Dirac statistics, which describe the behavior of particles known as fermions, continues to be a cornerstone in quantum mechanics. This theory has had a lasting impact on the study of condensed matter physics, particularly in understanding the behavior of electrons in metals and semiconductors. It also influenced the development of new technologies such as semiconductors and transistors, which are the basis of modern electronics. Fermi's legacy is also felt through the institutions and organizations that carry his name. The Fermi National Accelerator Laboratory, FMI Lab in Illinois, established in the 1960s, is one of the most important centers for high-energy particle physics research in the world. Fermi Lab has been instrumental in advancing our understanding of fundamental particles and forces, building on Fermi's early work and vision. The laboratory is at the forefront of research in areas like quantum mechanics, the search for dark matter, and the exploration of the Higgs boson, continuing Fermi's tradition of pushing the boundaries of human knowledge. Another facet of Fermi's legacy is the generation of scientists he inspired. Fermi was known not only for his intellectual brilliance, but also for his exceptional ability to mentor and inspire young scientists. His laboratory at the University of Rome, as well as his later work at the University of Chicago, attracted many future Nobel laureates who were shaped by his insight and example. Fermi's approach to science, rigorous, innovative, and often focused on solving practical problems, was deeply influential to many physicists who went on to become leading figures in their own right. His mentoring style emphasized collaboration, respect for different viewpoints, and the importance of combining theory with experiment. Perhaps one of the most remarkable aspects of Fermi's legacy is his reputation as both a visionary scientist and a modest, approachable figure. Despite his extraordinary accomplishments, Fermi was known for his humility and his ability to explain complex scientific concepts in clear and accessible terms. His genuine curiosity, deep sense of integrity, and dedication to advancing human knowledge made him a beloved figure in the scientific community and a model for generations of physicists. In the broader context of science and technology, Fermi's influence extends into disciplines far beyond nuclear physics. His work has had profound impacts on medical science, engineering, and even environmental sustainability. The principles he helped establish regarding the use of nuclear energy continue to be central to debates on clean energy and climate change. As we continue to explore the possibilities of nuclear energy and particle physics, Fermi's work remains a cornerstone in understanding the fundamental forces of nature. In sum, Fermi's legacy is not just one of groundbreaking scientific discoveries, but also of profound cultural and technological shifts. His impact continues to resonate across a wide array of scientific fields, and his example remains a guiding light for future generations of researchers. Whether in the realms of nuclear energy, particle physics, or the advancement of technology, Enrico Fermi's influence endures as a testament to the power of human intellect and the pursuit of knowledge. In closing, Enrico Fermi's life and work serve as an inspiring reminder of the transformative power of science and curiosity. From his groundbreaking discoveries in nuclear physics to his pivotal role in the development of the first nuclear reactor, Fermi's contributions have shaped the world in profound ways. His legacy continues to influence not only the scientific community, but also the fields of energy, medicine, and technology. Fermi's ability to bridge theory and experiment, his dedication to advancing human understanding, and his mentorship of future generations of scientists have left an indelible mark on history. As we look to the future, we must remember that his work was driven by a deep commitment to knowledge and a desire to improve the world, even when faced with difficult moral questions. His life encourages us to pursue curiosity, collaborate with others, and use our discoveries for the greater good. Enrico Fermi once said, "There are no secrets in science, only the mystery of the unknown." It is this sense of wonder combined with a tireless pursuit of truth that made Fermi a true pioneer. As we continue to explore the frontiers of science and technology, may we be inspired by his example to push the boundaries of knowledge and to approach the challenges of our time with the same ingenuity and passion that Fermi demonstrated throughout his remarkable life. Thank you.